4,000 years before the first computer, Babylonian mathematicians calculated square roots by hand. On clay tablet YBC 7289, cuneiform marks along a diagonal hide a stunning secret. Decoded, those marks translate to 1.41421, the square root of 2, accurate to 5 flawless decimal places. No calculators, no algebra, no electricity. Their algorithm was so perfectly optimized that the CPU inside your smartphone uses virtually the same logic today. And the craziest part? It is so simple, you can do it in your head. Let us steal their formula. Say you want the square root of 17. First, find the closest perfect square. That is 16, which belongs to 4 squared. To build the adjustment, do 2 things. For the top of the fraction, subtract. 17 minus 16 is 1. For the bottom, take your root 4 and double it to get 8. Put it together. 4 plus 1/8 equals 4.125. The true value is 4.123. 2 seconds of mental math, accurate to 2 decimal places. This formula is bulletproof. Try square root of 69. The nearest square is 64, giving 8 plus 5 over 16, which equals 8.312. Now try 111. The nearest square is 100, 10 squared. Subtract to get 11, double 10 to get 20. 10 plus 11/20 equals 10.55. But what if the nearest perfect square is larger than your number? Take square root of 23. The closest square is 25, which is 5 squared. Does the trick break? Not at all. Our base is 5. Numerator, 23 minus 25 gives -2. Denominator, double 5 to get 10. 5 plus -2/10 equals 4.8. So how did the Babylonians reach 5 decimal precision? They used a concept that forms the backbone of modern computer science: recursion, an infinite feedback loop. Find square root of 2. The nearest square is 1, so our first pass gives 1 plus 1/2, or 1.5. That is a weak estimate compared to the real 1.414. The Babylonians did not stop there. They fed 1.5 back into the same formula as the new initial guess and ran the numbers again. Square 1.5 to get 2.25. Divide the error by double the guess. The second loop instantly spits out 1.416. One more loop hits the tabulated value. But why does doubling the root in the denominator actually work? It feels like a trick, but geometrically, it makes absolute sense. Imagine a massive square whose total area is S. Inside, we draw our guess square with area A squared and side length A. The missing area left over is this L-shaped border, which we will call B. To approximate how much wider the guess square must expand, the Babylonians sliced this L shape in half into 2 equal rectangles, one pasted on the right, one on the top. Each rectangle has a known length A and an unknown thickness X. Because there are 2, their combined area equals 2 times A times X, which we set equal to B. Isolate X by dividing, and you get exactly B over 2A. That thickness, B over 2A, is the exact fractional adjustment we have been adding to our root this entire time. Ancient geometry perfectly maps onto modern calculus. 4,000 years ago, humans carved the foundation of coding into mud. Smash subscribe and drop the next math anomaly below.